Hello, my name is Aisha, and I will be introducing the photoelectric effect. Albert Einstein proposed that the behavior of light should not be described as only a wave. Instead, it could be better described as light being made up of discrete particles called photons, which are massless packets of energy that carry a specific quantum of energy proportional to a light's frequency. The photoelectric effect is a phenomenon from which electrons are ejected from a material surface, typically a metal, after having a light shone on it. The emitted electrons are called photoelectrons. This concept is studied in quantum chemistry as it demonstrates the quantized nature of energy, as the process of electron emission is made possible through the transfer of energy from light photons to surface electrons. The key conditions for photoelectron emission includes threshold frequency, work function, and light intensity. These will be demonstrated utilizing a web-based photoelectron simulator. The first simulation will be our control, with the conditions set to 50% light intensity, wavelength of 400 nanometers. The selected metal is sodium. Because wavelength and frequency are inversely related, increasing the wavelength decreases the frequency. In this simulation, you can see that increasing the wavelength to 550 nanometers causes photoelectron emission to stop altogether. Work function is defined as the minimum energy required to remove an electron from the surface. Each metal has a unique work function. This is demonstrated by switching the selected metal from sodium to calcium. Notice that under the same conditions, calcium is emitting way less photoelectrons than sodium. This is because calcium has a higher work function than sodium, meaning it requires more energy for electrons to start moving. The relationship between light intensity and photon emission is directly proportional. You can see this in the simulation. As light intensity is increased to 100%, there are way more photoelectrons being emitted from the metal.
We will be talking about a real-world application of the photoelectric effect. Solar panels are used in our everyday lives constantly, from powering homes to lighting to heating, etc. Solar panels convert sunlight into electricity using the photoelectric effect. This is possible because solar panels utilize solar cells, which are made up of semiconductor plates that have an electric field with a positive and a negative side. These are often made up of silicone because it's efficient and affordable. Electrons are ejected from the semiconductor when light hits them and then recaptured so that they complete a circuit. Once that circuit's completed, a current will flow and generate electricity, which helps power our homes. Another application of the photoelectric effect are photodetectors. Photodetectors are essential in digital cameras as well as scientific instruments, and they work by converting light into an electric signal. Photodetectors are a type of sensor, and they are what make it possible for digital cameras to convert photons into images. When the light hits the sensor, the electrons ejected are stored in a pixel grid that turns them into a voltage. This is then able to produce a number which can be converted into the images that the camera produces. Any scientific equipment that uses light measurement also utilizes photodetectors. Things like spectroscopy machines, such as the IR or UV vis, are only functional because they have photodetectors in them. Third and final application of the photoelectric effect that we will be discussing is one that can actually save lives. Photoelectric smoke detectors use light scattering to detect fires. When light and smoke interact, the light is scattered by the smoke in various directions. These smoke detectors contain a light inside of them that trips a photodiode sensor when fire is present. The smoke from a fire will scatter the light source in the detector, which is then converted into an electron. If the frequency is high enough, the electron is ejected and becomes a current that sets off a warning alarm. Normal household smoke detectors are ionization detectors and are more prone to false alarms from steam or fumes from cooking in the kitchen. Because photoelectric detectors specifically focus on how light scatters when interacting with smoke, steam and other fumes that aren't made up of big enough particles to scatter the light are not registered, and therefore make the photoelectric detector a more efficient option. The photoelectric effect relates back to a lot of what we talked about in class, especially in topics such as quantization, electromagnetic radiation, and the development of quantum theory. One thing that the photoelectric effect illustrates is that energy is not continuous, it's quantized. In other words, energy comes in fixed packets called photons. Einstein's explanation of the photoelectric effect shows that each photon has an energy of E over h nu, and that only photons with enough energy can knock electrons out of a metal. That means if the light's frequency is too low, no matter how bright the light is, no electrons are released. This directly supports what we learned about how energy levels in atoms and molecules can only take on certain values. The photoelectric effect also connects to our discussions on electromagnetic radiation. We usually describe light as a wave, but this effect shows its particle side, which is what we call wave-particle duality. It's the same idea that helps us understand how electrons behave as both waves and particles in systems like the hydrogen atom or the particle-in-a-box model. Seeing how light and electrons share this dual behavior really brings together the different parts of the course, how radiation interacts with matter on a quantum level. The photoelectric effect is one of the key concepts that actually led to the development of quantum theory. Classical physics couldn't explain why the energy of ejected electrons depended on the light's frequency instead of its intensity. The photoelectric effect essentially marks the point where physics shifted into the quantum era, which is the foundation for everything we've been learning in this class so far.